Quito. The floor is yours.
All right, so good morning, everyone. Thanks for joining us early today. And so today is our second lecture about Floquet engineering. Okay, let me close it. And let's start from where we left last lecture. So before that, some quick announcement. The homework set is available. So homework is at the web page. We are going to discuss the homework this afternoon, but some exercises are for later, not for now, but all the exercises are already there. And so this afternoon we have the homework or exercise session during the afternoon for this particular course. And I also included some references for the first lecture, so there is also a different file with references for the first lecture. I'm following some reviews, I'm combining them. So basically this Oka and Aoki, Oka and Kitamura from 2019. Bukov also has a review paper and his PhD thesis and so on, but all the references are there. I will put lecture by lecture what are the references, and hopefully eventually the lecture notes, but I will not promise when that is going to happen. But for now, you have references lecture by lecture, okay? All right, so we left yesterday finding the effective Floquet Hamiltonian. Effective Floquet Hamiltonian. And we found that this effective Hamiltonian could be written as a big matrix. And this big matrix had things along the diagonal, H0. And we were connecting now different photon sectors. So we had like omega 0 minus, H0 minus omega, H0 plus 0 omega, H0 plus omega. But all the sectors were connected now, in principle, with this H minus 1, H minus 1, H minus 2, and so on. H1, H1, H2, and so on. And the challenge was to diagonalize this big matrix and find the quasi-energies. So this is a concept that we also introduced last lecture, the quasi-energies. And we were able to do that for the spin 1/2 case. We did that everything analytically. We found all the energies. For your homework, one exercise is to do the same thing for a spin 1. A single spin 1. You're going to find out that it works for any value of spins, because basically it has to do with what I'm going to tell you now. You can always go to a rotating frame. So whatever we're going to do first in this lecture is something that you probably learned in your course when you took quantum mechanics, but we're going to do it again today. And the idea is that we can eliminate some time dependence by going to a frame that rotates together with this periodic potential. So just thinking physically, so let's say that we have X and Y and Z here, and we have something that rotates with some frequency omega t here. It could be some type of light, for example, circularly polarized light would do this. The vector, the electric field rotates along a particular plane. But you can go to a rotating frame, you can sit here, and rotate together with the source. If you do that, you're going to find an effective Hamiltonian that is time independent. So the question is the following: if I do this, if I go to a rotating frame, do I find anything that resembles what I find here by diagonalizing the Floquet matrix? Because these two approaches should be, in principle, equivalent. And the answer is yes. So the first thing that I will do today, I will go to a rotating frame, and I will find that the same energies that I found here, I would also find here. And for that, I will solve again the spin 1/2 case. All right, so this is the idea of going to a rotating frame. In principle, a rotating frame could eliminate time-dependent terms. We're going to see that it's not going to eliminate all the time-dependent terms. Otherwise, this thing would be unnecessary. But sometimes it becomes significantly simpler, and in some very specific problems, you can eliminate the time dependence completely by going to a rotating frame. So this is something that you probably learn in quantum mechanics. We're going to do this fairly quickly. So what is the idea? The idea is that you have a Hamiltonian, as usual, that satisfies Schrödinger's equation. It's the same equation I wrote yesterday, up to factors of h bar that are, at this point, completely eliminated. Well, and what we can do, we can apply a unitary transformation to this Hamiltonian. We're going to have, during this week, many different symbols and notations. So U, I'm going to refer to U as the unitary that goes to a rotating frame. To a rotating frame. Not to be confused with U, the time evolution operator, okay? This is the time evolution operator. These are two different things in principle. All right, so if I apply this unitary here, I can already put U dagger here. Very good. This is equal to the identity, of course. Psi, this is equal to I. And then here, I'm going to do this U dagger. And I'm going to insert, once again, dt of U dagger psi. Okay? Exactly. So h bar is 1 or h bar. These are the two possibilities, okay? All right. Very good. All right. So here we can just, this Hamiltonian is going to be changed to U dagger HU, U dagger psi. And I'm happy with this term here. This is okay. But now I have to apply the same idea here, just differentiating these terms. And what you get is the following. So you get I, U dagger, U dt. I will call this psi bar, U dt of psi bar plus dtu psi bar. Okay? All right. I can move this term to the other side of the equation and get U dagger HU minus I U dagger dt of U psi bar is equal to what? Is equal to I, and this is the unit again, dt psi bar. Okay? Very good. And this is an effective Hamiltonian. So I'll define an effective Hamiltonian in this rotating frame as U dagger HU minus I U dagger dt of U. This is an effective Hamiltonian. And this effective Hamiltonian follows Schrödinger's equation. So Schrödinger's equation for this Hamiltonian is H effective applied to psi bar is equal to what? Is equal to I dt of psi bar. So this is a new equation for this effective Hamiltonian. This effective Hamiltonian, in principle, could be time dependent. But in principle, could also, for some very special cases, be independent of time. And it's going to become very clear when this Hamiltonian is independent of time. It requires something that rotates like this. If you have a potential or something that rotates exactly like this, we can just sit here and the Hamiltonian has to be time independent. But this is not always the case. We're going to see this later. Very good. So this is the rotated Hamiltonian in this rotated frame. What is the point of doing this? It could eliminate time-dependent terms, but also another thing is that may help convergence. And this will become clear in a minute. Convergence of what? Convergence of the perturbation series. I will expand everything here today in power of 1 by omega. So you're going to see here we're going to do some large frequency expansion. So for large frequencies, a natural parameter is some energy scale of the problem, let's say some J, some energy scale, divided by omega is much less than 1. J, some energy scale. It's going to become much clearer later, but this transformation is useful. We can do Floquet engineering on top of this, or maybe this transformation already solves the problem completely, okay? For the case of the spin 1/2 that I told you yesterday, this transformation is sufficient to solve the problem. It's the simplest problem that we can solve. So yesterday, recall that we have a Hamiltonian for a spin 1/2 of the following form. Bz sigma z plus b parallel sigma x cosine of omega t plus sigma y sine of omega t. This term here is rotating exactly like this. Okay, this term is rotating exactly like this. So we have hope that we can eliminate the time dependence completely, and we can in fact do that. So the unitary that does this job can be parameterized by two numbers, t and t0, and I will give you the answer, but it's not hard to guess what the answer is. You just have to go to a frame that rotates with omega t, and you want to eliminate this this term here, so it's going to look like a rotation. It's a rotation with a time periodic, or with a time-dependent angle. So you just rotate around the xy plane. So how do you do this? You do this with exponential of minus I sigma z by 2. Recall that our rotation would be with sz here, so sz is sigma z by 2, times omega of t minus t naught. Okay? T minus t naught. There's not much question that this is going to work, because again, you are just rotating with an angle that has the same rotation period as this time-dependent term. If you do the algebra here, so the exercise is to just, let's call this equation 1. So using equation 1, it's a trivial exercise. It's just a rotation of the Hamiltonian using this time-dependent angle. You get the following. You get an effective Hamiltonian that looks like Bz minus omega by 2 sigma z plus b parallel sigma x cosine of omega t0 plus sigma y sine omega t0. Okay? All right. Completely time independent. You're going to ask me, well, but there is this t0 here. This t0 is a constant. So t0 is some arbitrary constant time. It's the initial time, okay? It's the initial time. This omega by 2 comes from this last term here, okay? The time derivative will give you this omega by 2. And this thing comes from the rotation, from U dagger. This comes from the U dagger, HU, okay? Interestingly, this Hamiltonian, but also it has to be like this. The spectrum of this Hamiltonian is very easy to find, and the quasi-energies have the exact form as we found yesterday. So it's plus or minus square root of b parallel squared plus bz minus omega by 2 squared, okay? It will not have the constant term in front. The constant term, you may recall, just tells you in which Floquet Brillouin zone you are, Floquet zone you are. But this gives you a gap. So the gap, that would be E plus minus E minus, is the same as yesterday. Same as from the Floquet Hamiltonian that we wrote yesterday, okay? That's why if you're studying quantum mechanics in grad school and so on, you learn this, and it works, it's fine. And it's completely consistent with what we did yesterday. But many examples that I will write down today cannot be solved using this. There is no rotating frame which would eliminate the time dependence completely. And then we have to do that prescription. Do you have questions so far about this? All right, so the homework has you have to do everything again for the spin 1 case. Very good. And finally, something that will be useful for later, I can tailor expand this epsilon plus and minus. We know how to solve this problem. So we can tailor expand the square root and so on. And we can compare later with the same solution, but using perturbation theory. So you can tailor expand this. And I will leave you as an exercise maybe to find these coefficients. So it's something proportional to omega, something constant, and something that goes as 1 by omega. So as an exercise, let's put as an exercise, you can calculate these numbers, okay? It's just Taylor expanding the square root, because then we can compare the numbers that you get here with the numbers that we're going to get by doing perturbation theory. So these two things have to be the same. It's just expanding the square root in powers of 1 by omega. Okay, so this is the error. The error is of order 1 by omega squared. Okay, if omega is very large, we are going to be studying some cases today in which omega is very large. All right. This is all that I had to say about the spin half case, but I think it's very instructive for the other problems we are going to solve. And now we are finally going to start solving or trying to solve perturbatively some problems that cannot be solved like this. But for that, let me just introduce you to the high frequency expansion. I will not do the entire algebra for this, just because the algebra is identical to what you do when you take quantum mechanics, and then you have to do degenerate perturbation theory. So just as a warning, this is basically degenerate perturbation theory. So this is degenerate perturbation theory. And again, when we are going to do perturbation theory, we need a small parameter. So for the high frequency expansion, as the name suggests, the small parameter is the inverse of the frequency. So 1 by the frequency is a small parameter, but obviously this is not dimensionless, so this is not a legit small parameter. So the small parameter is going to be, again, this j significantly less than 1. And I already defined j here. I will not do it again. J is a generic number. You can call it W. It's something that tells you the energy scale of your problem. If you have a tight binding problem, it could be the bandwidth. If you have an interacting problem, it could be the hopping divided by some other parameter. Something comes here. In my example, if you want to do the perturbation theory, it would be BZ. BZ. To be safe, I would say BZ by omega, B parallel by omega, both much less than 1. But maybe there is a special combination that you only need the square root, probably, very likely. Yeah, by looking at the first terms of the expansion, you're probably BZ. But yes, these two numbers would be much smaller than 1. And then you can Taylor expand everything. All right, so how do we solve this problem perturbatively? So we go back to our matrix here. If we go back to our matrix, we can decompose this Floquet Hamiltonian into 2 parts. Okay, into 2 parts. So the Hamiltonian can be written as, the Floquet Hamiltonian can be written as something that has only terms along the diagonal. So let's say minus omega, let's put it even more, minus 2 omega, minus omega, 0 omega, 2 omega, plus everything else. And everything else is huge. It's going to be the H0, 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 and so on, and the H minus 1, H1, H minus 2, and you populate all this entire matrix with everything that is left. So everything that is left comes from this matrix. And what is the idea in this perturbation theory? The idea will be to consider this as the unperturbed Hamiltonian, unperturbed, and this one as the perturbation. Okay? This will be a perturbation of this term. After you make this decomposition, everything else follows naturally. You perform here the same perturbation theory that you would do when you're taking quantum mechanics and you have a degenerate manifold. Okay? So what is the size of this manifold? Again, for the spin half, each block, or each Mn, I'm calling this Mn now, is a 2 by 2 matrix. This is the simplest possible case. It could be 1 by 1 even. You can do this approach for the cases in which you have a single level. You can also do that. But the spin half is slightly more interesting. So it's 2 by 2. And now I'll just write down what are the equations order by order in perturbation theory. And I will leave you as an exercise. But again, it's identical. You can open up any textbook. You can open up Cohen-Tanuji, for example, and it's going to be there. It's the same equation. All right, so the effective Hamiltonian in perturbation theory is the following. To lowest order is H0. So I choose a target manifold here. So let's say I want to correct one of these guys here. Okay, I want to see corrections inside this manifold of 0 photons. I will basically integrate out all the other sectors. Okay, let's say this is the 0 photon sector. It corresponds to this. And I want to integrate out over everything else. Okay? So the next term in this series is the sum over m not equal to 0. First thing that we know here, it has to have 1 by omega. Basically, you start from here, you visit some sector, and then you come back. It's always like this. Yes. No, it's the same. Is it looking different? This matrix should be the same as that matrix. No, this matrix is infinite. So here there is H0 minus 2 omega, H0 minus 3 omega. It goes forever. Forever. This is a gigantic matrix completely populated that goes forever. So this n goes, this number here, m, goes from minus infinity all the way to infinity in steps of 1. So this matrix is an infinite matrix, okay? Yes, absolutely. You're completely correct. Yeah, let me do it here slightly more careful. So this has the identity matrix here, the identity matrix, identity, 0, so what is this? This should be a 1. Omega times the identity. Yeah, the identity has the dimension. Here for spin half would be identity 2 by 2. But in more challenging problems, all these blocks can be huge. No, sorry, it's not. No, now we are back to Floquet. Back to Floquet. Yeah, the rotating wave, the rotating frame started there and ended here. We solved this problem, okay? Later, we can combine both. We're going to combine both. You have a time-dependent Hamiltonian. First, you rotate, and then you eliminate some terms, and then you still have a periodic Hamiltonian, and then you do this. That is, you can combine them, but they are not identical. No. I'm back to that initial Hamiltonian. Any other questions about this? This one is HF, yes. Yeah, this one, okay, this is the result. So this is a gigantic matrix, as I was telling you. So there is this label M that goes from minus infinity to infinity, and thinking of the spin half, you also have 2 degrees of freedom, so each block, let's say in this case, is 2 by 2. And now what I'm trying to do, I don't want to handle this gigantic matrix, so I'm going to do perturbation theory. In order to do perturbation theory, I have to have a target space. So I have a space in which I want to know the physics in that particular space. And this particular space, H is going to give H effective. So H effective lives inside here. So H effective will be 2 by 2. Will be 2 by 2. In this, again, 2 by 2 just because we're talking about spin half. It can be huge, but I'm going, in other words, you can say that I'm going to integrate out all the other Floquet sectors, and I want to find an effective low energy theory that lives inside this 2 by 2 block. Of course, it will know about the other Floquet sectors, but again, it's a theory for this particular 2 by 2 problem. So this H effective is the one that you find in perturbation theory, So let me, let me call PT, perturbation theory. Okay, this is what you'll find in perturbation theory. Okay, so if I, just to draw in a little bit of detail what I'm writing down here, let's say that you have these 0 photons. You have 0 photons, which corresponds to m equals to 0. What is happening here to this order, I didn't write the answer, but what happens is that you can absorb m photons and then re-emit the photons. So you can, by absorbing photons, you can transition from this guy to some block and then come back. And again, this is always like this in perturbation theory. These are the virtual states. These are the excited states that you visit, and then you come back to your ground state. So here you can absorb some number of photons. Let's say I absorb 2 photons. If I absorb 2 photons, I come here. There, I come here. And then I re-emit the 2 photons, and then I come back. So these are the excited states. And I'm summing over all these possibilities. The answer is, this gives H minus M, HM minus HM, H minus M. Okay? This is basically absorbing and emitting photons, and this is basically emitting and absorbing. And the minus sign comes because you can go here first or here first. Okay? Plus some terms of order 1 by omega squared. 1 by omega squared. This is a little bit gigantic, this next correction, as it often happens in perturbation theory. If you go to some higher orders, you get more possibilities. I may write it down in a minute, but we'll see. But I would like to, what I would like to become clear at this point is what I'm doing here, okay? I want to find an effective Hamiltonian that will know about all these other Floquet sectors, but that will live inside a particular sector, like this one, of 0 photons, okay? And this is the correction in powers of 1 by omega. Questions? Because you can first absorb 1 photon and then you come to omega and then re-emit. So this is a plus. Or you can first come here and then come back. And this is a minus. Because of these guys have opposite signs. Absolutely. The energy denominator can be plus or minus omega. So this one has an energy denominator that is plus omega, and this one has a... Oh, sorry, I forgot. This is divided by m, sorry. You are completely correct, and the energy difference is m times omega, not just omega, of course. Yes. No, I didn't put a half here. Oh, sorry, that's why. Yes. Thank you. Is this what? Yes. We can discuss the origin of this factor of 2 later. Yes, there is a factor of 2. The factor of 2 is, we can discuss this in more details later. I think it comes from the structure of the perturbation. It doesn't come from the energy denominators. I think it comes from this expansion in the perturbation theory. That's right, yes. Okay, that's a shorter answer, yes. The energy difference is basically, if you go to 1, it's 1 minus minus 1, something like this. This is what you mean, right? Yes, that's right. We can discuss this in more details, but the energy difference between these states is 2m omega. Do you agree as well? Yeah, we can discuss this half later. We can discuss this half later.
The half because you are summing positive and negative. So you have the same term twice.
Yes, yes, that's right. Yes, yes. Any other questions about this?
Do you need to write down as structure? Because, as you said, you could just one of the terms and erase the half.
No, it helps because this is a commutator. This is going to be very helpful when doing algebra.
Okay, so that's just for helping the algebra.
Yeah, right. Yes. Yeah, I agree. This half, I agree. It's from double counting. Yes, this half is from double counting. Any other questions about this? Is this structure clear? Very good. We are going to be using this equation in several different examples. Okay, so let's go to our the first example that we cannot solve. The first example that we cannot solve is a generic tight binding model. So let me introduce what a tight binding model is, and then we can look at these corrections here and see if it's giving different physics. So remember, our point here is to find physics that was not initially present. So we had, let's say, a tight binding model that I will define now, and the question is, can we find corrections to this tight binding model that is going to make it more interesting? And we're going to do this with graphene first, and then we're going to talk about a 1D system later. But the point, always keep that in mind. You don't need to be able to solve this as we did for the spin half. But you can still find interesting physics by assuming, and this is an assumption, that the frequency is very large, and then you can follow this approach. And this approach is more or less easy to handle. H0, we know what it is. So you recall that H0 is just the average. H0 is 1 by the period, 0 to t dt of the time-dependent Hamiltonian. So this is very simple. And these guys are also simple. You just add the exponentials here. So these are just the Fourier components. So this Hamiltonian is not so complicated. And this is a big step. Okay, so now let's try to analyze what's going on in some simple cases. So the first case that we are going to address is, again, the tight binding Hamiltonian. Okay, so the tight binding Hamiltonian has the following form. So let's assume some general Hamiltonian that has the form Hamiltonian is equal to sum over I and j, j, I, j, ci, dagger, cj. So this is a time-independent Hamiltonian. A time-independent Hamiltonian. And again, I know that some symbols have many different meanings. One of them is this H. I'm calling several things H. But for now, let's assume this is an operator that is time-independent. And this ST means stationary. So it's some Hamiltonian that does not depend on time. Okay, typically also, when we are handling systems like this, you would call this TIJ, the hopping TIJ. It's much more common. But we have a problem here, and this is really an issue because we have time dependence. So we are going to avoid calling hoppings by T. Okay, and that is a problem later when I start talking about Heisenberg models, because I'm using J already. But this is a problem for tomorrow. For today, this is a hopping term. Okay, so TIJ, stationary, are hopping terms. Hopping terms. So if you're not familiar with this notation, this is a second quantized notation. All you need to know is that if I have a site I here and a site J here, this operator is going to remove a particle from J and bring this particle to I. And the Hamiltonian has to be Hermitian. So surely there is another process that will do the reverse. Okay? So these JIJs, you can choose them. You have to choose them carefully to make the Hamiltonian Hermitian. This entire week, the Hamiltonian is going to be Hermitian. I will not be talking about non-Hermitian Hamiltonians, okay? Right, but let's say, so you have a bunch of, these are I and J, so I and J are going to be site indices. I and J are, one of them is a site index. And let's say that this Hamiltonian is a little bit boring. You know how to solve it, nothing interesting happens. So what we can do next, we can make it time dependent. So let's make it time dependent. So we now have a Hamiltonian which is an explicit function of time, sum over I and J, Jij of T, Ci dagger Cj. Okay? Where Jij of T is equal to Jij of T plus big T. So this Hamiltonian is clearly periodic, and we can solve it. We will not be able to solve it exactly, but we can definitely solve it by doing this perturbation theory. So the equation that we have to recall is, I'm going to write it here because I'm going to delete that equation in a moment. So it's H0 plus sum over M not equal to 0 of this commutator of minus M and M divided by 2M omega plus something else. So just to leave it here. It's a great advantage, as I was telling in a moment, to write this as a commutator, because commutators are nicer to calculate, and we can eliminate many terms if they commute. All right, so our task is to take this Hamiltonian and use this equation to convert it into something that we can treat. That's not very hard. That's not very hard. We have all the technology that we need. I'm going to just revisit in case you already know this by heart. You don't have to take note again. But recall that this can be decomposed as 1 by t, the integral 0 to dt, e to the I m omega t, j, I j. Sorry, this is going to be with the m here, m, j, I j of t. Okay? Exactly. 2 pi by omega is the big frequency. And what is the assumption here? The assumption here is that this Jij stationary divided by big omega are significantly less than 1. So I can use here. So I have all the ingredients that I need. All the ingredients that I need are here. So we're going to do several examples with graphene and so on, but I think it's important to do this formally first, and then we can just use the equations over and over again. So Jij, maybe I have to write down the Hamiltonian first. So the Hamiltonian is going to have terms that come from the expansion, and it's going to have the following form. It's going to have terms that are Jij0. Let me see what is the notation here. No, these are different things. Jij0 is the average of Jij. You mean, so let me just see what is the notation that I'm going to use. I'm going to use the notation that Jij of m. So for example, Jij of 0, just to put the notation, is not equal to Jij stationary, okay? Because Jij0 is the time average of this thing here.
Your assumption involves Jij stationary.
Yes. My assumption involves Jij stationary, so I can.
You didn't say what's Jij of t. That's what matters, right?
Right, no, the assumption is this, I'm assuming. This is the assumption that Jij stationary by omega is much less than 1. It's just a hopping term, initial hopping term. Let's say that you have a lattice, and then the electrons can move around, and this is the time-independent problem, like in regular graphene. So Jij stationary would be just the hopping in graphene, some number, right? And now we are going to make this thing oscillate. So it's going to oscillate, and I'm going to have a function here, which is an explicit function of time. I will define later. It can be any function. And then I take the Fourier components, and they are going to give me Jij of m, okay? Like if this is, let's say that an example, it could be a cosine. So it could be that, just as an example, that Jij of t is J stationary times cosine of omega t, if you want an example for it. This is an example.
You should say Jij maximum value of Jij is over omega is much less than 1. That's the safe assumption, right?
Right. If all of them are less than 1, in particular, the largest is much less than 1. Okay. Very good. Questions so far? It typically is. It's just the hopping around a particular lattice. Right, it can be a problem. It could be, the problem can happen, for example, and we're going to consider this probably on Friday, the small frequency expansion. There's also a case, let's say that this Jij are, just to give you some spoilers, these Jij are typically hopping terms on a lattice, and they are of order of some, not larger than electron volts. Not larger than electron volts. Definitely not larger than electron volt. And this omega can be the frequency of light. It can be milli-electron volt, it can be electron volt. So there is room for this assumption to be valid, and there is room for this assumption to not be valid. And we are going to consider both approaches. And today we are considering, by construction, the approach in which Jij is much smaller than omega. Is it necessarily like this always? No, but if you know, for example, for graphene, you know these numbers, and then if you go to a lab, you just choose the frequency to be much larger. And then you have the assumption being fulfilled, okay? All right. So this, let me write one equation before writing this. And again, we are going to do several examples, but I think it's important to do it formally first, because otherwise we keep doing the same thing over and over again. So the effective Hamiltonian is going to look like this. And this is the effective Hamiltonian, that is this. And I will show a little bit more about this, but it's the sum over I and j of Jij 0 plus Jij1. The notation is going to become a bit heavy, but plus Ci dagger Cj. Okay, so we start with a Hamiltonian that looks like this. And we are going to end up, I'm telling you, I'm not showing it yet, to end up with an effective Hamiltonian that is going to look like this. Where are the Floquet fields? Again, we integrated out all the Floquet fields. So it's obvious that this Hamiltonian does not have any m dependence. These are all integrated out. Floquet field is just any periodic potential. We call it a Floquet field. In this case, it will be the J cosine of omega t. Any time-dependent perturbation is integrated out. We call it a Floquet field. It's just a periodic potential. Just a periodic in time potential. So this is all integrated out. The effective Hamiltonian is going to look like this. So the question is, what are these coefficients? And these coefficients, I'm going to write them like this. And I will try to be careful with notation here. If you find something strange, let me know. This Jij0 is J0. So you know how to calculate J0. You just come here and you do this. This one is easy. It's completely consistent with this term here. So this comes from here. Okay? It's just the time average of your Hamiltonian. So this is the 0th order term. Jij1 is more interesting. So Jij1, you just compare it with this guy. It's going to be sum m not equal to 0, sum over k, JIK minus M JKJM divided by M omega. And this one requires explanation. So this first one does not require much explanation. It's just you come here with your time-dependent Hamiltonian, you find H0 by doing this thing here with M equals to 0, and you're done. So it's the time average. This is the time average of the Hamiltonian. This one requires an explanation. Why am I calling this J1? So here in general, Jij L, let's say, is going to be proportional to 1 by omega to the power L. Okay, this is what I'm calling J0, J1, and so on. Okay? The question that is left is why does Jij of 1 have this form? It's not so obvious. It's almost obvious. That's interesting, yes. See if this helps. It's a property. It comes from basically here. No. This term has to be Hermitian. I think if you take the dagger and use this property, you should get the same thing. You open up this commutator, it's going to have two terms, take the dagger, and then maybe you're going to take m to minus m or something like this. We can discuss during the coffee break, but this... That's right. That's right. So you can make m to minus m if necessary. And then it should be Hermitian. No, exactly. I think we discussed this. This is actually where this half comes from. Because it is, writing it here has great advantages. One of them, the commutator is nicer to calculate because it already filters many terms. And also, it's sum over all m's, positive and negative. So that's why, end of the day, you got this half, okay? More questions? Okay, so bunch of notations. So this guy with the bracket is proportional to this, and this guy without a bracket is the Fourier component. What is not obvious is this structure here of J1. Okay, this I'm telling you. I will just motivate a bit more. In case you haven't seen the second quantized notation, I'll just tell you how to get this, just to do a little bit of algebra, how to get this term here, because end of the day, the majority of problems that we're going to be solving here, the term that is doing something nice is this term here. Because the other terms are subleading. We can discuss the other terms later. They're subleading, and in many cases, they just do the same thing as Jij0. So they are subleading and not very effective. But this term is the dominant term besides this H0, and it can be extremely interesting. Okay? So the way to do it, let's represent schematically what's going on. So if I have a lattice and I have sites I and j, what is going on with this term here is that I'm just hopping from I to j or from j to I with some amplitude that is now Jij of 0. Jij of 0. Nothing much is happening. This is the process that I'm representing here is Jij 0. Nothing much is going on. Nothing much. In some cases, this can be interesting because it can completely suppress this hopping. It can make it vanish. It's called dynamical localization. We can discuss this a bit later. But you can cook up some Floquet potentials, some time periodic potentials in which this goes to 0. They call it dynamical localization. This has been experimentally verified in cold atoms. Okay, and also you can have I and j here. But now I want to discuss the physics of Jij1. So what's going on with Jij1? So Jij1, you go from I to j, sure, but you make a stop first. So let's invoke the site k here, some other site k. And then instead of going directly, let's say that you couldn't go directly, let's say. Or if you could, just here. But now you can make a stop. So you come here first, and then you stop, and then you come here. And then you arrive. And the process in which you come from here to here, you can absorb photons. So the photons come here. I'm already using this word. I mean, any time periodic potential, I will call it a Floquet potential, and I will refer to everything as photons. Even some time periodic potentials don't have anything to do with photons, but I would just call them generically photons. So you can absorb M photons here, and then you re-emit the M photons here. Okay, you re-emit. So this is it's called a photon-assisted process. Photon-assisted process. Okay? Photons. So in terms of just representing graphically, this is what is going on. But now you have to do the algebra, right? I will just tell you some steps of how to do this algebra. And again, it could be that in principle, these two sides are not connected. If these two sides are not connected, they can become connected via some intermediate site. And it could also be that it's going to be the case for graphene, that this part here is okay, but now if you put some type of light, the system becomes chiral, for example. This is interesting, and we're going to talk about this in a moment. Okay, so let me see what we can do in terms of algebra for this process. For that, I'm going to tell you this. What I'm going to tell you in the next 2-3 minutes has nothing to do, or very little to do, with Floquet engineering. It's basically a tool that you can always use. It's very useful in case you're just starting working with the second quantized Hamiltonians and so on. I will just write 2 or 3 equations that are going to make your life significantly simpler. I will make an assumption here that is not completely necessary, but I will assume that we have fermions. You can do the same thing with both. This is a non-interacting Hamiltonian. It's fine, but I will be working with interacting Hamiltonians later, and all of them are going to be fermionic. So the fermions follow some anti-commutation relations that are like this, in case you have never seen them. These are the anti-commutation relations followed by fermions in the second quantized notation. If you're not familiar with this, just keep it for the future, and then in some years you can revisit these notes after you take the proper courses that teach you how to do this. I'd just like to point out to this very useful equation that solves this problem, basically, if you have never seen this before. A, B, C, D, minus C, D, A. B plus C, A, B, D, minus C, A, B, D. Okay. With these 2 equations, you can completely solve this problem and find this effective Hamiltonian here. This effective Hamiltonian. Okay? You just take a generic term, for example, I'm not going to do the entire algebra, but you take some term like this, Ci dagger Cj. Here you have to commute them. So you have the j's effective, but these j effectives are multiplying the fermionic operators. So you have to commute the fermionic operators, C, K dagger, Cl. Okay? And maybe if you have never done this calculation before, you could in principle fear that you're going to end up with something with 4 fermionic operators. You're not. You're going to end up with something with only 2 fermionic operators because you're going to use this equation here. And in particular, if you just plug it here, this term will disappear, this term will disappear. Okay? And then, end of the day, you just need these first 2 terms. And these commutators are going to give you numbers, C numbers, they are called. It's just 1 in this case. And then you end up with bilinear fermionic operators. This is a simple exercise that is completely complementary to what we are doing here. Exercise is not Floquet. This exercise is more related to the the strong correlation part of this course. Okay, just to put you the result, you can verify this. It's very simple. JKL CI dagger CL minus CK dagger CJ delta LI. Okay? This is a commutator, yes. This is an anti-commutator. This, just to define it, so the anti-commutator of B and C, or any two objects, is BC plus CB. This is an anti-commutator. Okay, this is a notation. Fermions anti-commute, so we define this object here. Okay, it's just to give you some way of doing it. But for this problem, if you are not familiar and you want to derive this very nice equation, you can also write down the Hamiltonian as H equals to sum over Jij stationary Ij, if you prefer to work like this. Sometimes it's even easier, to be honest. You just do this and you continue with life. I mean, it's a non-interacting Hamiltonian. This is the first quantized form, and this is the second quantized form. All right, if you just plug these fermionic operators into this equation here, you trivially get this result. Trivially get this result. Okay? Is it clear? Okay. You commute them. You're going to have the fermionic operators to commute. You end up with a new fermionic, a new bilinear with this, the product of these two couplings. Okay. The factor, I will leave you, maybe there, it depends on how you are summing here. There may be a factor of 2. I will not guarantee this factor. Let me just think a bit about it. No, but it depends on how you define this, these I and J's here as well, if you're summing I and J and I and so on. I can be more precise later. When we have a lattice, we can be significantly more precise about this. But if you're summing I and J and then Ji and so on, you may or may not have it having the factor of half.
But so far, you're summing over all I and over all J.
That's right, over all I and all J. Yeah, I will. In that case, I will put the factor of half, I guess. I will put the factor, yes. Very good. Any other questions? Okay, so formally this is what we have to do, but now we can see this in practice if we can find some interesting physics using this. The homework, another exercise for later that I put in the homework is to compute. It's not horrible, but it's a little bit of extra algebra to compute this. Okay, to compute this. And the idea is that you can stop twice now. You can stop twice. You can have a K, you can have an L, and then you stop twice. And we may need this for some specific problems later. Okay? All right, so now...
The process of coming back, it cancels out identically, or?
No. No, it's Hermitian. No, no, no. It's...
We need to go IK and KI back. So I can be equal to J.
I can be equal to J, for example, yes. But
Right, so you can have on-site.
you can have on-site. Yes, you can have on-site, yes. You can. There is a limit in which this K you can drag all the way to here, and this K can be here, right? Yes, and I can be equal. Sure, and you can make I equals to J. All the combinations are possible, yes, at this point. So that's why we're going to do some lattices, and we're going to discuss in more detail what these things mean. Okay? So this is one of the exercises, And another exercise is to do this for a square lattice. That's the simplest. We are going to do this for the honeycomb, motivated by graphene, but you can for sure do this for a square lattice. You take a square lattice, like this. So this is also homework. And just to go back to Andre's question, you have a hopping term here. Let's call it, we call it J stationary. So only nearest neighbors and all equal. So this has also J stationary. I don't need to put indices because they are going to be nearest neighbor and equal. And what you discover is now that you can have a stop in the middle, you can connect these two terms directly. So there is an effective hopping now between these two terms. Okay? So you had only nearest neighbors. Only nearest neighbors. We call it NN in equilibrium. But if you add Floquet, we have next nearest neighbors. No. You always go and come back.
So you divide the two lattices. You have two independent lattices. You can cook graphs on that Jij0 is 0.
Mm-hmm.
Then you get an effective model in which you have two independent sublattices connected.
Right.
Next nearest neighbor interaction.
Right. Right. So, okay, I agree. So this guy is going to be proportional to J stationary squared, probably. Yes. Over omega. What I was arguing is that even if you put you don't need a cosine for this, because you're going to sum over all the Floquet sectors. So if you have a time periodic potential that is more complicated than a cosine, you're going to decompose in Fourier modes, and you're going to integrate out over all of them. So you'll just sum more. But the fact that it's a next nearest neighbor comes actually from the lattice indices, from this contraction here. So any periodic potential that you put, Floquet nearest neighbor of order 1 by omega. That's what I meant. The term 1 by omega, if I do this, it's going to be like this.
But I'm saying that if you put a Floquet field
Uh-huh.
as average mean, you don't have the Jij0. And then you always break the lattice. Because you have to go to one lattice and come back. So
Yeah.
sublattice A is connected to sublattice A, sublattice B is connected to sublattice B only. That's a property of these lattices.
Yes.
Right?
Yes. Yeah.
And your
Y-
frequency expansion
Yeah,
is always even power of perturbation theory.
Yes.
So you have to go and come back.
You have to go.
Always the same sublattice. You never go from one sublattice to another. That's easy.
Right. Yeah, that's true. That is true.
Okay, that's
Right.
side.
Right. But no, but the next term here in the expansion, the zeroth order term already renormalizes this guy. This is A to B. The average of Jij.
Yeah, that's what I'm saying. If the average is 0,
If the average is 0, then this guy is 0.
yeah.
Okay, fine. That is a possibility, yes.
The third term, the omega cube is 0 again, and so on.
Yes, absolutely. Exactly. So these are going to come back to us when we talk about the knobs in Floquet engineering, what we can choose, what we cannot choose. But this simple example of the lattice already tells you a lot about these possible knobs. Again, what Neto is saying is that you can choose this to be 0, for example. You can choose a special type of Floquet field such that this is 0. Or even this ratio, you have the ratio of these two couplings. Probably on Wednesday or on Thursday, I will try to maximize this ratio. I want to make this as large as possible and this as small as possible. Why? This will become clear later. But the idea here is that you can play with these couplings now. Okay? You have ways of calculating these two things. And I suggest strongly that during this afternoon, you try to do this. Square lattice is not complicated to do this for the square lattice. I gave you all the ingredients. But during the afternoon, please try to do this and find these numbers. You're going to get a better feeling of what's going on with these choices of cosines or sines and other possibilities. Okay. All right, so now we are ready to move to graphene. Graphene is the first lattice, and we have all the ingredients here. All the ingredients here. So let's see what happens for graphene. This is the second half of this of today's lecture. Okay, let me continue from here. All right, so this is very formal so far, but what can we do in practice? In practice, you have graphene. Graphene is always nice to work with. So we have graphene. So graphene is made of carbons. These carbons form a honeycomb lattice. And the maximum I can draw is this. I mean, I cannot, if I start drawing the other honeycombs here, I will get confused. But this is enough for us today. So this honeycomb profile has hoppings. So the idea here is that you have a collection of electrons. I'm not going to derive the microscopic model for graphene. What I'm going to tell you is that you have carbon layers, or just one sheet of carbon, and you have electrons that can move around in this particular honeycomb lattice. And as Neto was asking before, you have the sublattice structure here as well, AB, B, A, B, and so on. So you can basically put colors on each site, and each site can be like this or like this. Or not colors, circles, let's say, like this, this, in such a way that A only talks to B, and B only talks to A. So you can put like colors or circles in such a way that the hoppings, so we are going to have hoppings here. And for now, I will change notation. I had these J's before, because I was trying to be very general with J, IJ, and so on. But for graphene, we have hoppings that are nearest neighbor hoppings, which means that the only thing that these hoppings can do, and I'm going to call them TH. And the only thing that this TH can do is to take you from A to B or from B to A. This is done via TH. And there's a TH here, and so on. You can always move around, but only nearest neighbors. This is what is found for this particular material, okay? And again, I'm not going to tell you the microscopics. So this part is given to us. We have a time-independent model for graphene. All right, and what is the Hamiltonian of this time-independent model? The Hamiltonian is the same as before. I'll also bring a minus sign here in front of the hopping term. It's typically written like this. Ij, Ci dagger, Cj. Following the same notation as before. Electrons. These are electrons moving around. So this operator destroys an electron in J and brings it to I. This is what this operator does. It's Hermitian, and this sum means that I and J are nearest neighbors. You sum over all the possible nearest neighbors. So if I fix this site A, I will sum over here, and here, and here, and so on. As was the case here, the question with the factor of half, you always have to be careful about double counting, okay? Don't double count. If you have an electron moving from here to here, then if you sit here, don't count this process twice, of course. You can only count the process once. Okay, so I will draw the lattice probably again, because now I want to write down the vectors. So we are going to define 3 vectors, delta 1, delta 2, and delta 3. And these vectors will all have the property that they are going to connect A to B. So if you sit here, this vector connects A to B, via delta 3, A to B via delta 1, and A to B via delta 2. So these are the vectors that connect the nearest neighbors. Okay? All right, so the next step that we have to do here, okay, I can rewrite this Hamiltonian as minus TH, sum over I and sum over delta, AI dagger B, I plus delta, plus BI plus delta dagger AI. Okay? This is just rewriting this Hamiltonian in terms of this notation A and B, where A and B live on each sublattice. Okay? So the A's here, so in each sublattice A, I will define a second quantized operator AI, and in each B, some operator BI. I is some arbitrary index. Okay? Such that the I, this index I, will only run, actually, I'm sorry, to be precise, this would be B plus delta 1, like this, just to be precise. The I will run over the A sites. I runs over A sites, or it's called sublattice. Runs over the A sublattice. And then you don't have double counting. You sit here, and then you sum over these three vectors. And then you sit here and sum, and so on. You count all of them and all of them once. Just my suggestion when you face Hamiltonians like this, lattices, just draw the lattice and manually see that if you just look here, okay, this is connecting to these three, so I already count this, this, and this. Now I will sit here, okay, I'll sit here, I'll count this, this, and this. And then you easily see that you are counting everybody. Just a suggestion, because otherwise the algebra, you can make mistakes if you don't see what's going on. Something that I will not teach you today, but it's also taught in any solid state course, is how to solve this Hamiltonian. You solve this Hamiltonian by going to momentum space. So by going to momentum space, I will assume that you know how to do this from quantum mechanics. So instead of solving this in real space, you have hoppings in momentum space. You don't. So K is, again, almost a good quantum number up to vectors of the reciprocal lattice. But this model for graphene can be solved. And what is interesting, and then when you solve this in momentum space, what you get is what we call band structure. We get a band structure. Band structure, in case you have never heard this word before, this is going to tell us what are the eigenvalues of this Hamiltonian, okay? For the eigenvalues of this Hamiltonian. If you just take this, if you go to momentum space, it's a Fourier transformation, you're going to get the following thing. H is going to be equal to minus TH, sum over delta, e to the minus I, delta K, BK dagger AK, plus the Hermitian conjugate. If you haven't ever seen this before, just ask me during the coffee break or during the afternoon, during the exercise lecture. Okay, anything that you have never seen before, because I won't have time to do this carefully. Okay, and we can rewrite this as minus TH, AK dagger BK, 0, F star of K, F of K, 0, A, K, BK. All these K's are vectors, okay? Delta is vector. Let me be slightly more precise here. There's no reason not to be precise. So these K's are vectors in 2 dimensions. Yeah, here, thank you. Thank you. And sum over K, sum over K. All right? So now we are defining these new fermions, AK and BK, in momentum space. So the same way as I told you that Ci dagger creates a fermion at site I, BK dagger creates a fermion with momentum K. Okay? Same as AK. They both create fermions with momentum K, but they have this A and B are called sublattice indices, as I told you before. They come from having A and B here. So we have two flavors of fermions of momentum K. And then we can diagonalize this Hamiltonian. It's still not diagonal. If you want to find the band structure or the energies, you have to diagonalize this Hamiltonian. It's almost diagonal. It's significantly better than before. This is a hopping Hamiltonian. Here you have KK, KK, so it's diagonal in K. Very good. But not yet fully diagonal. This is not a diagonal matrix. But this can be diagonalized very easily. And I will tell you what the eigenvalues are. Exactly. So this function f is a very simple function, in fact. So this function f has the following form. F of k is sum over delta e to the I k dot delta. K dot. It depends on delta, it's summed over delta. Something that I will probably do next, or later today, or probably next lecture, is that you can rewrite this delta I as well. Or this delta, let me use another letter, as A. This A is a serious candidate to be set to 1 as well. This is the lattice, this is the distance between the atoms in your lattice. So this is called lattice spacing. So A is some lattice. It has nothing to do with the other one. It has nothing to. So I will immediately set this to 1. A, I'll set lattice spacing. Everything is measured in units of the lattice spacing. Okay, so this can be written as cosine of phi L and sine of phi L as well. And you can already see the angles. You can do the trigonometry. Phi 1 is pi by 3. Phi 2 is pi. And phi 3 is minus pi by 3. Or if you prefer, you can go the other way around. Okay? When you do this Floquet engineering calculations, any calculation, it's much simpler to work with these angles. You're going to see why in a moment. Okay, but this function f of k is defined here, very good. And we can diagonalize this matrix now. The matrix is a 2 by 2 matrix, we know how to diagonalize. It turns out that the dispersion, epsilon of k squared, is f of k squared. That's all. That's all. The eigenvalues of that matrix are the square of this. It's obvious. You do minus lambda, then you find the eigenvalues. So far, this procedure would work for any tight binding model. So if I give you another lattice, what you do is you go there, you write these A and B operators, you go to momentum space. So far, so good. What is interesting about graphene is that there are two special points that I will tell you which are these points. These points are big K equal 2 pi by 3, 1 by root 3, and K prime 2 pi by 3, 1 minus 1 root 3. And these are points in so-called reciprocal lattice. So these are points in momentum space. These are specific values of K. Let me put it here. At K equals this, and K equals this, what happens is that f of K equals either to K or K prime is 0. We say that this model is gapless. This model is gapless. So you have states with 0 energy at this point. Okay? You just evaluate. This is also a very simple exercise. End of the day, what you have to, you write down these as cosines and sines, or whichever way you want, and then take the dot product with these things. You evaluate this f, it's identically 0. And if you Taylor expand the dispersion around this, you get the so-called cones, Dirac cones. So if you go around, around k and k prime, in the neighborhood of k and k prime, you get a linear dispersion. And these are the Dirac cones. It's called Dirac cones. It's a cone like this that is centered around this value, k or k prime. Again, you make these plots of energies in momentum space, and you find out that around k or k prime, you get this Dirac cone. This was very novel and interesting in the early 2000s. It was even possible to do this, to grow this material, to grow graphene, and it led to a Nobel Prize in physics. What we're going to do in this lecture is to take this model that we know how to solve it, just solve it here, and do the Floquet engineering, and see what can we get on top of this. So this we already have. But what happens if we apply this prescription here to this model? And we basically did everything that we had to do, because we did everything formally here. It's just a matter of evaluating now. You just evaluate these functions for the honeycomb lattice. But then it comes the question, realistically, which Floquet potential should I choose? How do I choose the Floquet potential? And the answer to this question, you can choose the Floquet potential that you would like to choose. That's your choice. But experimentally, there is one choice that is significantly easier to probe or to construct in a lab. That is to apply light, radiation, to this sample. So the way we draw it is the following. So you take graphene. So here's graphene. It has honeycombs. I can draw one, okay. And then you have the Floquet field. So the Floquet field or the Floquet potential. And I'm going to assume that we have a Floquet potential that is going to be light. Electromagnetic radiation, okay? Electromagnetic radiation. And this electromagnetic radiation will have a propagation vector. I will not write k, because we're already writing many k's here, but light propagates in a particular direction. So this is the propagation direction of light. And I'm going to assume that light propagates perpendicular to the sample. Graphene is 2D. I'm going to have my laser pulse. I take graphene, laser pulse, shining light perpendicular to this plane. And then I gave you all the ingredients that you need to solve this problem. I'm already telling you what is the time-independent Hamiltonian. I'm already telling you what is the Floquet potential. So you have all the ingredients. The last thing that you can ask me is what are the properties of this light? I didn't tell you everything about the light. Let's say that light is circularly polarized light. We write it here, so circularly polarized light. And you can choose left or right polarization. So recall that if you look at in one particular plane, circularly polarized light, just a comment about electrodynamics. Now, if you have light and if someone tells you you have circularly polarized light, it means that the electric field rotates on a particular plane, either this way, or it rotates this way, okay? One of them is left, and one of them is right circular polarization. So one of them is right and left, depending if you're looking from top to bottom or bottom to top. But for us, it won't matter much. So these are circularly polarized light. The electric, when we talk about polarization, we are talking about the electric field. Electric field. Okay? So the electric field is a vector, E of t, and this electric field rotates. And this gives you the polarization of light. Just recapping that polarization of light is a property of the electric field, and the trajectories that the electric field is making on a particular plane or in space, or this gives you the polarization of light. For us, the most interesting one is going to be circularly polarized. I'm going to explain in a moment why. So I'm already telling you the polarization. And as usual, let's assume that this light has frequency omega. Frequency omega. So I already told you polarization, circularly polarized. Frequency, omega. Is there anything else that you would like to know about the light to do the calculations, besides omega and the polarization? What else characterizes the electromagnetic field? The amplitude, the intensity. Amplitude or intensity. Amplitude or the intensity, or some people call it the fluence. The fluence. The amplitude I'm going to call A0 for reasons that will become clear in a moment. So this is the protocol. We call this the protocol. I told you yesterday about choosing the knobs in Floquet engineering. I'm choosing, these are my knobs. I can in principle change this, I can change this, and I can change this. But I definitely can do calculation beginning to end with this information here and this information here. And when I say beginning to end, it doesn't mean that I'll be able to solve the Hamiltonian completely. But I can definitely do perturbation theory the way we did and find what is the effective Hamiltonian. This can be done easily. We have all the ingredients. It's just a matter of writing it down. The only physical step that we have to do before that is we have the light, great. We have graphene, that's also great. But now what I need to do is to couple them. This is the only thing that I didn't tell you how to do. Okay, I have the model for graphene here. I'm shining light. So light, very clear, graphene, very clear. How do they couple? Well, they couple the same way as you couple gauge fields with quantum mechanics. You do it by minimal coupling. You minimal couple them. Okay? So it's the standard coupling of electromagnetic radiation with electrons. Okay? And the way we're going to do here is the so-called power substitution. I will tell you what is the substitution and give you all the ingredients. And then tomorrow afternoon, third lecture, we completely analyze what is the physics here. Okay? And then you're able to solve basically any non-interacting problem using the Floquet technology. Okay, so the way they couple, it's called the Paros substitution. In which, going back to the notation of J's for a moment, because I want to be generic at this point, this couples as Jij stationary exponential of minus I integral from one point of the lattice to the other point of the lattice of dl times A of t, where A of t is the vector potential. This is called the vector potential. It's another thing from electrodynamics. E of t is minus dt A of t. And since we are talking about electrodynamics, I have to warn you that I'm also going to make C equals to the E equals to 1. So one more thing that is going to be equal to 1. This equation here, if you have never seen this before, this is the lattice version of the standard minimal coupling that you see in quantum mechanics that basically boosts k in momentum space going to k plus a of t. Okay? These two things are completely compatible. Okay? If you may have seen this earlier in classical mechanics even, how to do this coupling, okay, the minimal coupling. And this is the latest version. It's called power substitution. Wikipedia has a very lengthy discussion about how these things are compatible, and Feynman even gave some arguments of how to show easily that these things are equivalent. In terms of algebra, you just see that they are. You can, for graphene, you can do this, and then you can do this, and you just compare, okay? You just compare. All right. I'm basically out of time for today, but it's maybe almost a good point to stop. All the ingredients are given here. What happens to the band structure? What happens to the topology of graphene? So the questions, I'm going to leave you with questions so we can start tomorrow answering them. You have all the ingredients at this point to answer them without me, but in any case, we are going to be doing this tomorrow. So the questions are the following. What is the effective band structure? So what is the effective band structure? Gapped, gapless, topological, chiral. So we can answer all these questions about the band structure that comes from this procedure that we just had, okay? I will not give you the answers, but you can pick up the most interesting possibilities here. It's going to be the most interesting possibility of these combinations here, okay? All of them, it's gapped and gapless. Yes. Yes. Questions? Okay, so. Mm-hmm. It's easier with light. Okay, the answer. Okay, so just to rephrase, the question is why light, right? I mean, it could be some other oscillating field. It could be an oscillating chemical potential. It could be even mechanical oscillations. It could be. It is possible to do many of these choices. Experimentally, light tends to be the easiest. Why is it easier than an oscillating chemical potential? I'm not completely. The effects are not identical. The effects are not identical. Light has several advantages. Several advantages. If you exactly knobs, and the most interesting, and that's why this field of Floquet. This is not the only reason, but one reason why this became so popular is because it's going to be the answer of this example. How Danny proposed in the 1980s a model in which you would have what we now call a turn insulator in a very specific setup, honeycomb lattice. What was eventually discovered, and this is the answer to this question, is that you naturally get this if you do this protocol here. So it's extremely interesting. Can you get this with other setups, like with these capacitors or oscillating chemical potentials? Maybe, but what I will highlight tomorrow is that the chirality of light. So the light here is CP, the circularly polarized light is intrinsically chiral. And that's why you get many things that are so interesting. The light already provides you the chirality that you need to have this. This may be the hardest one to find of all of this. And this this can be done experimentally, number one, and number two, provides especially the possibility of being chiral. This is a good one. I will show you with the algebra how this chirality from light is transferred to the lattice. But for now, you just have to recall from electrodynamics that a circularly polarized light, unlike linearly polarized light, is intrinsically chiral. it rotates forever in one particular direction. Other questions? Yeah, because there are, it is my choice, but it's a good choice. Why? Because you may recall something that I will be completely neglecting here. I didn't do the algebra, so it's not completely obvious yet, is that when you write down the vector potential of light, you have e to the I, k, let me put KL as in k light, r, I, some position, plus the omega t term. I want to neglect this term. I want to neglect. What happens if if light propagates perpendicular to the sample? This is constant, basically. I mean, if k only has z component, let's say perpendicular along z, it's only kz. And then all the r's are along the xy plane, so this is a constant. Nowadays, people are also considering along the sample direction, but then you have to use that this k is very, very tiny for light. So even if you do along this direction here, you may be able to neglect that phase. That phase is not so great because it's position dependent. So it doesn't. This prescription wouldn't work if you were to consider the explicit dependence on lattice positions. Okay, but this can be neglected even if you put light along this particular direction. You have to do this if you're considering a 3D sample. So this was done in the context of topological materials that are three-dimensional, and they may not be very thick. Sometimes they are like thin films, and then you just neglect some of those terms. Okay, but perpendicular is the most natural choice. Other questions? All right, so we resume for exercises this afternoon, and then the third lecture is tomorrow afternoon. All right, thank you.